everyone. Let's wait for 5 minutes before we start the session. Okay, so today we'll be discussing problems of week 6 assignment sheet. which are mainly related to the differentiability of real valued functions and limit continuity of multivariable functions. So let's start with first question. Question number one. Fix some x naught in R, which is non-zero. Let f be a function defined on R to R, be differentiable at x naught. That means f is differentiable at some non-zero point. Now for every m in R, we define the function am, which is from R to R, defined as follows. Amt is equal to f at t x naught minus f at x naught upon t minus 1 times x naught minus m. Now state whether true or false. There exists m in R such that the function am is continuous at t equals to 1. So basically we need to see whether if this function am can be continuous at t equals to 1 or not. So for continuity, we know that this limit should be equal to the value. That means limit t tending to 1, amt should be equal to 1. Now we can see that at t equals to 1, we do not know the exact value of the function am. But still, if this limit exists equal to the value of the function am at 0.1, and hence the function will be continuous. So our aim is to see whether this function am is whether this limit t tending to 1 am exists or not. For that, we will be using the differentiability of function f, because somehow this function am is dependent on the function f. Let's see. Now, since f is differentiable at x naught, since f is differentiable at x naught, then by the definition of differentiability, this implies that limit h or limit x tending to x naught, fx minus fx naught upon x minus x naught exists, and this is equal to the derivative of f at x naught. Okay, so equivalently, if we look at the epsilon delta version of this limit, we can say that this implies for any epsilon positive, there exists some delta, which obviously depends on the on epsilon positive, such that this mod fx minus fx naught upon x minus x naught minus f dash x naught. Yeah, because f is differentiable at x naught, this f dash x naught is a finite value. So we can write it like this. this will be less than epsilon whenever mod x minus x naught is less than delta. Okay, so let me mark this as equation 1. We need to see the continuity of the function am. So for that, am at point t. So that means we need something am minus some L to be less than epsilon whenever mod t minus 1 is less than delta dash, something like this. So for that, let me now let t belonging to R be such that this modulus of t minus 1 is strictly less than delta by mod x naught. We'll see how this will be useful for us. So if I take t to be any real number which is in a neighborhood of 1, so basically if this is 1, we are in between 1 minus delta by mod x naught to 1 plus delta by mod x naught. So we are taking t somewhere from here. So that will give us, this implies the modulus tx naught minus x naught, which is equal to mod x naught times mod t minus 1. This is strictly less than delta. That means tx naught is in delta neighborhood of t, sorry, of x naught. Listen, that is mod tx naught minus x naught. This is less than delta. Now, whenever this is happening, by differentiability of f, this condition should hold. That means by first mod f, now this x should be replaced by tx naught. So that means f tx naught minus fx naught on tx naught minus x naught minus f dash x naught. This is strictly less than epsilon. Now that means mod f dx naught minus fx naught upon t minus 1 x naught minus f dash x naught minus 0. This will be less than epsilon whenever we started with mod t minus 1 less than delta by mod x naught. Whenever t minus 1 is less than delta by mod x naught. And clearly, since this delta was taken from the definition of, this delta was taken from the definition of differential, this limit, it depends on epsilon. So somewhere this upper bound also depends on epsilon. And taking m to be equal to f dash x naught, which is obviously belonging to real number, we get mod amt minus 0. This is less than epsilon whenever mod t minus 1 is less than delta prime, where delta prime is nothing but delta by mod x naught. Therefore, defining amt to be equal to ftx naught minus fx naught upon t minus 1 x naught minus m. Here this m is actually equal to f dash x naught, and this is for whenever t is not equal to 1 and 0 whenever t equals to 1. So this, if I mark this equation as 2 by 2, since epsilon positive is arbitrary and delta prime equals to delta by mod x naught depends on epsilon, we get limit t tending to 1 AMT equals to AM1. And this is happening for m equals to f dash x naught, which is a real number because f is differentiable at x naught. Therefore, the given statement is true because they were saying that there exists some m such that am is continuous at t equals to 1. So basically for m equals to f dash x naught, this am is, yes, continuous at 1. Therefore, the given statement is true. I hope the solution is fine with everyone. If you have any doubt, you can ask. The main idea is to use the definition of differentiability of the function f in order to prove this continuity of the function an. So yeah, you can go through the solution once again. If you have any doubt, you can ask. I'll wait for 2 minutes. Okay, then let's move to next question. Okay. State whether true or false. Let f be a function defined from a b to r, be differentiable such that the derivative such that f dash is bounded on the whole interval AB, then the limit, so we should say the limit extending to a plus fx and limit extending to b minus fx both exist. That gives us an idea that maybe we can extend this f up till the bound on the boundary of the domain as well. So in this case, this is a well-known result. I hope you all know that if a function is differentiable and the derivative is bounded, the function turns out to be Lipschitz continuous. I mean, I hope if you are familiar with the term Lipschitz continuous, we'll see that in detail. So that Lipschitz continuity eventually gives us the uniform continuity, and for uniformly continuous functions on the open interval AB, we all know that the limits on the boundary exist. So yeah, I'll be proving that in detail how we get that. So main idea is to use the property of the uniform continuity of this F in this case. And yeah, let's see how we get that. Since F is differentiable and the derivative F dash is bounded on open interval AB, this implies there exists some positive real number such that it happens to be the upper bound of the function f dash, such that mod f dash x is less than equal to m for every x in open interval A. Okay, let's mark this as equation 1. Now we'll be using the mean value theorem. Let x and y belonging to open interval AB be arbitrary. And without loss of generality, we can assume either one of them to be smaller than the other one. Something like this. Yeah, arbitrary, and we are taking both of them now to be equal. So now, since f is continuous in closed interval xy, because obviously xy is strictly inside this boundary, inside this open interval AB, and since f is differentiable, therefore it is continuous as well. And f is differentiable on open interval xy. Now this gives us the conditions for the mean value theorem. Then by Lagrange mean value theorem, there exists some c which is in between xy such that this f dash c is equal to fy minus fx upon y minus x. Now this gives us, or instead I should write it on the other side. This is equal to f dash c. Now if I take modulus on both the sides, since f dash is bounded for all x in for all points in open interval AB, and c is in xy, which is a subset of AB, so this is less than equal to m. This gives us, since x can never be equal to y, so x minus y is non-zero, so taking it in the denominator. Moreover, we can multiply both the sides, so that would give us mod fy minus fx is less than equal to m times mod y minus x. Now this property is called Lipschitz continuity. So I'll mark this as equation 2, and for your information, any function satisfying this equation first is called a Lipschitz. The spelling might not be correct. Please check whether this is fine. Yeah, if it's wrong, please let me know. A Lipschitz continuous function. And in fact, any Lipschitz continuous function is uniformly bounded, uniformly continuous. We'll see that also. So now, yeah, and this is happening since we took arbitrary x and y in AB. This is happening for every x and y in open interval AB. Now let x and y in AB be such that mod x minus y is less than delta. What delta to be taken specifically, we'll see that later. Now suppose mod x minus y is less than delta, then by first we get mod fx minus fy. This is less than equal to m times delta. So taking delta to be strictly less than epsilon by m, and further taking epsilon to be any arbitrary, and for any arbitrary epsilon positive, we get mod fx minus fy strictly less than epsilon whenever mod x minus y is less than delta, where obviously this delta is depending on epsilon. That gives us the definition of uniform continuity. Therefore, this implies that this f is uniformly continuous because this x and y are arbitrarily taken from the domain such that the distance between them is less than delta, and that delta is eventually depending on epsilon. This implies that f is uniformly continuous on open interval AB. Next, we will be using the property of uniform continuity to show that the limits at the boundary also exist. For that, we will be using the sequential criteria. So let me change the color. Oh, yeah, same. Now let xn be a sequence in open interval AB such that xn converges to A. So obviously xn can go to A from right hand side only because our domain, this is A, this is B. We are taking points from here only. We cannot take points from left hand side of the A. So that means basically this xn is converging to A plus because from we are tending towards A from the right hand side. Now, if we are able to show that this sequence fxn is convergent to some fixed real number, that will give us that this limit exists. Now, since xn is converging to A, that means the sequence xn is Cauchy. This implies xn is a Cauchy sequence, and we know that every uniformly continuous function maps Cauchy sequence to a Cauchy sequence. Is a Cauchy sequence in open interval AB. Now, since f is uniformly continuous, this implies the sequence fxn is Cauchy as well. And since we are in the set of real numbers, we all know that every Cauchy sequence is convergent. Hence, there exists some real number L such that this sequence fxn converges to L. Now, since we started with an arbitrary sequence xn converging to A, by sequential criteria, since we started with an arbitrary sequence xn converging to A, by sequential criteria, we get limit extending to A plus fx will be L. Now I would like you to try it yourself using this again same arguments to show that the limit extending to b minus fx will also exist. Using same arguments, show that limit extending to b minus fx exists as well. I'll give you some time. You can try it yourself. Following exactly the same arguments that had been explained for this limit extending to a plus, try to prove that limit extending to b minus fx exists. I can wait for 2 minutes if you want to try now. And let me know if you have any doubt. Okay, so do that yourself. So therefore, we get that the given statement is true. So the main idea was to see that if any differentiable function that which has bounded derivative is always a Lipschitz continuous function. So by Lipschitz continuity, we mean that it satisfies this kind of inequality, and hence the function will be uniformly continuous. Further, using the properties of uniform continuity, we get that both these limits will exist. Therefore, the given statement is true. I hope this is fine. If you have any doubt, you can ask. Or else, let's move to next question number 3. State whether true or false. State whether true or false. If f from a comma b to r is differentiable, such that f dash is bounded on open interval AB, then f is uniformly continuous on open interval AB. Now for this problem, I would like you to tell me. I have done exactly the same things previously. Tell me whether this is true or false. So yeah, we had seen this earlier, no? If f is differentiable, f dash is bounded, that gives us that f is Lipschitz continuous, and hence by using the epsilon delta definition, we get f is uniformly continuous. Therefore, the given statement is true. Okay, then let's move to next question. Question number 4. Again, state whether true or false. If f is a function defined on R2, that means it is a multivariable function. RT to R is a function such that the directional derivative the directional derivative that we write du f at 0, 0. So this is the directional derivative of f at 0, 0 along the direction of u. Direction of u exists for all unit vectors u in R2. Then they are saying that f, this function, such a function f should be continuous as well. Now, if you remember, in the case of one variable functions, when f is function defined on just the set of real numbers, in that case, if we are given that a function is differentiable, then for sure the function is continuous. But as soon as we move to multivariable function, the things are quite different. In this case, this such a thing need not happen. That means it is possible that the directional derivatives in all the directions are existing. They have some finite values, but still the function is not continuous. We'll look at some specific examples to see how this is happening. So for that, firstly, you should be well known to the definition of this directional derivative. So I'll just recall. how we evaluate this directional derivative in the direction of u. So if u is a unit vector given by u1, u2, since it is unit vector, then it has this u1 square plus u2 square equal to 1. So since it is unit vector, then the directional derivative in the direction of u for the function f at some point a, b is given by limit h tending to 0, f a plus h u1, b plus h u2 minus the value of the function at point a, b upon h. So I'll show you an example where this function will have directional derivative in all the direction. That means with respect to any unit vector u, you will be able to evaluate this directional derivative, but still the function will not be continuous. It will not even have limit at point 0, 0. So let's see solution. So if we define a function f from R2 to R such that fxy, this is equal to x square y upon x to the power 4 plus y square whenever xy is non-zero, and this is equal to 0 whenever xy is 0, 0. So let's start with the continuity of the function f at point at the origin. So firstly we'll check the continuity of f at origin. So when do we say a function is continuous at some point? A function is said to be continuous if now f will be continuous at origin if this limit xy tending to 0, 0 fxy is equal to f0, 0. Now we know that the value of the function at point 0, 0 is just 0. So we need to show that in order to see the continuity. If the function is continuous, then this limit should exist and should be equal to 0. So let's see whether this limit exists or not. So now when it comes to evaluating the limit in R2, so if you remember in the space when in the case of one variable, if, in order to check limit extending to x naught, we used to check the left hand limit and the right hand limit. So we used to see how the function is behaving if we take the values of x towards x naught from right hand side and left hand side, and if both these limits are same, then we would say that the limit exists. But now, when we go to this R2, now going to any point, in order to reach at some point, there are infinite directions. So I can go here from along x-axis, along y-axis, along this line, along this curve. There are so many paths to reach this point 0, 0. So a very good and very easy way to show that limit does not exist, just show them that there exist two distinct paths such that along these paths the values are different, the way we used to do in the one variable case. So if this LHS left hand limit and right hand limit are not equal, we would say that the limit does not exist. In this case, if we can show two distinct paths which passes through the origin, that means the path, for example, the path y is equal to x and y is equal to x square. Both the paths uh, pass through the origin, and if suppose if the function, if the limit is different in both the cases, then we can directly say that the limit does not exist. So in this case, let's see how this limit does not exist. So for xy tending to 0, 0, that means the function, the points xy are not exactly equal to 0. The limit is, no, limit xy tending to 0, 0, fxy, this is equal to limit xy going to 0, 0, and the function is x square y upon x to the power 4 plus y square. So if I am able to show that there exist distinct paths along which the limits are different, I'll be done. So if we consider the path y equals to mx, m can be any real number. I'll take that later. Then along this path, it becomes limit extending to 0, replacing y by mx, we get, sorry, we need to take mx square in this case. So that will give us m x to the power 4 upon x to the power 4 plus m square x to the power 4. So this will be limit x tending to 0. So yeah, this x to the power 4 gets cancelled out, just m upon 1 plus m square. And now everything is independent of x. This is just m upon 1 plus m square. Now this tells me that, tells us that if we approach the origin along the path y is equal to x square, taking m equals to 1. In this case, limit xy tending to 0, 0, fxy is here. Taking m equals to 1 here, this gives us 1 by 2. Whereas, if I approach via y equals to 2x square, in this case, this limit is equal to 2 upon 1 plus 4, 2 by 5. So basically, if I'm approaching origin via the points lying on y equals to x square, then in that case, the limit is coming out to be 1 by 2. And if I approach it via y equals to 2x square, in that case, the limit is turning out to be 2 by 5. That means the limit is not unique, which gives us a contradiction because limit should always be unique. Limit, we say that the limit exists only if it is same along all the paths. So therefore, limit does not exist. And hence, the function f is not continuous. Now, since limit is not existing, what can we say about continuity? So the function f is not continuous at origin. But still, we will see that in this case, the directional derivatives exist. I hope this is clear how the limit is not existing and hence the function is not continuous at origin. So basically, that's just the fact that along different paths, the limit is turning out to be different. So yeah, therefore the function is not continuous, but still we will see that in this case, the directional derivatives exist. Now let's next part is to check. Next, we need to check the directional derivatives. So let's start with some unit vector u. Let u1, u2 be a unit vector. So by definition, du, directional derivative in the direction of u of the function f at 0, 0 is equal to limit h tending to 0 f u1 sorry, 0. 0 plus u1h, 0 plus u2h minus f at origin upon h. So by definition, this is equal to limit h tending to 0. Since u1, u2 both cannot be 0 at the same time because u is a unit vector. So that means we are evaluating the value of function at some point which is away from origin. Therefore, by the definition of the function f, this is u1h square u2h upon u1h to the power 4 plus u2h square minus the value of the function f at 0, 0, just 0 upon h. So once we simplify this, we get this is equal to limit h tending to 0, u1 square, u2, h square upon, sorry, h cube. Yeah, that would be eventually cancelled out. Okay, so, let me write it first time. H cube upon h, and taking out h square outside, u2 square plus u1 power 4 h square. So this h cube gets cancelled out. We are left with limit h tending to 0, u1 square u2 upon u2 square plus u1 power 4 h square. Now, if u2 is 0, in that case, this denominator turns out to be 0, and we need to see what happens in that case. So we'll start with case 1. If u2 is non-zero, in that case, directly taking limit h tending to 0, we get this is equal to u1 square u2 upon u2 square, which is just u1 square by u2. Therefore, in this case, the directional derivative is exists. Now let's see what happens when this u2 is 0. Now since u2 is 0 and u is a unit vector, therefore u1 must be equal to 1. And that means the directional derivative is in the direction of 1 comma 0, direction of x-axis. That means duf at 0, 0, this is limit h tending to 0 f h comma 0 minus 0 upon h. And this by the definition of function, because if we take y to be 0, we have x squared by, so h squared times 0, so this is equal to 0. Therefore, in this case also, the directional derivative exists. Directional derivative exists in along all the unit vectors. Obviously, since we are taking unit vector u differently, it should depend on u. That means, yeah, in all directions, direction derivatives is existing, but still the function was not continuous. So therefore, for this function, the directional derivatives exist in every direction. In every direction, or we can say along every unit vector, along every unit vector, but it is not continuous. But the statement was saying that if the directional derivative exists in all directions, then the function must be continuous. Then, therefore, the given statement is false. I hope this is clear how we got the function to be discontinuous at origin and still having directional derivative in all the directions. Please go through the solution once again, and if you have any doubt, you can ask. I'll wait for 5 to 6 minutes. Okay, so if there is no doubt, we can move to next question. Number 5, again state whether true or false. Let f from R2 to R be such that the partial derivatives fx, fy exists on R2. That means partial derivatives exist for if fx exists for all a, b in R2. Similarly, fy also exists for all a, b in R2. Further, and further, the second order partial derivatives fxy and fyx also exists on R2 for all a, b in R2. Then they're saying that the derivative the partial derivative with respect to y of the function fx at ab is equal to fyx ab at ab for every ab in R2. So that means the second order derivative, no matter what the order you take, first to differentiate with respect to x, then y, or first live with y, then x, then that should not affect anything. But actually, that's not the case. That happens only when the function is very smooth. Such functions are called smooth functions. If the function is not smooth, then we cannot say whether these two will be equal or not. So, for instance, I can give you an example. Using that example, you can see that how this does not hold. Consider the function f defined from R2 to R as xy equal to xy times x square minus y square upon x square plus y square, whenever xy is not the origin and it is equal to 0 whenever when xy is the point origin. So we'll see that the partial derivatives for this function at point 0, 0 exist, both fxy and fyx, but they are not equal. So let's see how does it look like. So fyx at point 0, 0. So this is partial derivative with respect to x of the function fy, which is partial derivative of f with respect to y. So by definition, this is equal to limit h tending to 0, fy 0 plus h comma 0 minus fy at 0, 0 upon h. Now, in order to further evaluate this, we need to know how this fy, what is the value of f I'm so sorry, I got disconnected in between. Um, I hope my screen is visible now.
Yes, ma'am.
Okay. Okay, so we were evaluating the value of fy at h comma 0 minus f at h comma 0 will be 0 upon k. So this is equal to limit k tending to 0 hk h square minus k square upon k h square plus k square. This k and k gets cancelled out. So now taking k tending to 0, we will be left with h cube on h square, which is just h. Okay. And similarly, let's find fy at 0, 0. This is limit k tending to 0 limit k tending to 0 f at 0 comma 0 plus k minus f at 0 0 upon 0. So by definition of f, again this will be 0. Therefore this fy x at 0 0, this is equal to limit h tending to 0. Now fy at 0 plus h comma 0 was just h. This will be h minus fy at 0 0 0 upon h. So this is equal to 1. Now let's see what will be our fxyh. Now fxy at 0 0, this will be by definition limit h tending to 0 f fx um 0 comma 0 plus h minus f 0 0 upon h. Now fx at 0 0, okay, we'll have to evaluate fx at 0 comma h. This is equal to limit k tending to 0 f k comma h minus f at 0 comma h upon h, sorry, k. So this is equal to limit k tending to 0. By definition, fkh, this is equal to kh k square minus h square upon k square plus h square minus this will be 0 upon k. This we will be left. This k and k will get cancelled out. We're left with h k square minus h square upon k square plus h square. Now taking k tending to infinity, this time we'll be left with minus h cube. Sorry, Yeah, minus h cube by h square, which is minus h. And fx at 0, 0, this will be limit a tending to 0, f k comma 0 minus 0 comma 0 by k, and by the definition of the function f, this will be 0. Now using all this in above, so this implies fx y at 0, 0, this is equal to limit h tending to 0 minus h minus 0 by h. So in this case, this will be equal to minus 1. But if earlier it was 1. So this implies limit this implies fx y 0, 0, which is minus 1, is not equal to 1, where 1 was equal to fyx at 0, 0. So therefore, even though the derivatives exist, derivatives of second order exist, that this ordering can bring the change in the value. So basically fxy and fyx need not be same. I hope this is clear. Please go through the solution. And if you have any doubt at any point what about the calculations and all, please let me know. Okay, so if there is no doubt, we can move to next question. Question number 6. Let S be the set of points such that it contains all those x, y in R2 such that x square is not equal to y square. And F is defined on the set S to R. It is defined as follows. Fxy equal to x to the power 4 minus x square y square. Yeah, in the above problem, the given statement was therefore false. X to the power 4 minus x square plus y square upon x square minus y square. And this is happening for every x, y, and s. So I hope you must have understood why we defined the function f on the set S. Basically, if x square equals to y square, the denominator becomes 0 and hence the function will not be well defined. So further state whether true or false. The partial derivatives fx and fy both exist at every point in S. So this will be a good exercise to check the partial derivatives and using the definition, the limit definition of using the limit definition of partial derivatives. So we'll see. And yeah, if in that case the limit exists, then we can directly say that the derivatives exist. And if the limit does not exist, the partial derivatives does not exist as well. So we start with some arbitrary point x naught, y naught in S. So let's see whether the partial derivative with respect to x exists or not at point x naught. So by definition, if x naught, y naught, this is equal to limit h tending to 0, f at x naught plus h comma y naught minus f at x naught, y naught upon h. Now if this limit exists, we can say that the partial derivatives exist. So it's all just calculation. We'll see whether we'll firstly simplify this inside term. So this is limit h tending to 0. See the definition. So by definition, this will be x naught plus h to the power 4 minus x naught plus h square y naught square plus y naught square minus the value of the function at x naught, sorry, upon, no? Let me write it a bit smaller in size. This will be x naught plus h to the power 4 minus x naught plus h square y naught square plus y naught square upon x naught plus h square minus y naught square minus value at x naught x naught to the power 4 minus x naught square y naught square plus y naught square upon x naught square minus y naught square, everything divided by h. Okay, so this will be limit h tending to 0. Let's just expand, take this expansion. So we will have this is x naught plus h square plus h square plus 2x naught plus h. Sorry. X naught square plus h square plus 2x naught h whole square minus y naught square x naught square h square plus 2x naught h plus y naught square upon more simpler. We'll start with taking this LCM in the denominator. So this will be limit h tending to 0 x naught plus h to the power 4 minus x naught plus h square y naught square plus y naught square times x naught square minus y naught square minus x naught plus h whole square minus y naught square times x naught to the power 4 minus x naught square y naught square plus y naught square upon h x naught square minus y naught square x naught plus h square minus y naught square. So this will be equal to limit h tending to 0 so if I just expand this, this will be x naught square plus h square minus 2x naught h, taking x naught square common. So whatever is there with it, we'll take it one side. Minus x naught power 4 plus x naught square y naught square minus y naught square. Then taking y naught square common, we will have minus x naught plus h to the power 4 plus x naught plus h square y naught square minus y naught square plus x naught power 4 minus x naught square y naught square plus y naught square. Then we are left with 2x naught h, and with it x naught to the power 4 minus x naught square y naught square plus y naught square all divided by h x naught square minus y naught square x naught plus h whole square minus y naught square. Okay, so this will be equal to limit h tending to 0 x naught square. This is the first term is x naught plus h square whole square. So yeah, I can write it as x naught square plus h square plus 2x naught h whole square, and that we know that is equal to x naught power 4 plus h square 2x naught h square plus 2x naught square h square plus 2x naught h. So I'll write directly that only. This will be x naught to the power 4 plus I can take this h square outside, h plus 2x naught square plus 2x naught square, again h taking common, h plus 2x naught. Okay, I'll write this part. Then we have minus y naught square times x naught square plus h square plus 2x naught h plus y naught square minus x naught to the power 4 plus x naught square y square minus y naught square. Again the same, the first term just with negative sign. Everything divided by h. So the main thing is that all the terms that is not multiplied by h will eventually get cancelled out somehow, and you'll be left with things so that you can take this h common and inside then taking h tending to 0, eventually this limit will exist. Yeah, that will be a bit calculated. Let's see how much I can do. Let me take the terms that has h separately. Mhm. One second. Yeah, this is a bit calculative. I hope you can do it yourself, and eventually you'll get that this everything will get independent of h. Basically, the denominator h will get cancelled out somehow from the numerator, and all the terms without left without h will be taken, and eventually this limit will exist. This will be a good exercise because I my screen size is small. I don't know whether I'm not able to do that here. Or we can do one thing, you can try it yourself, and in next class, you tell me whatever answer you're getting so that I'll match it with my calculation. Okay, then we'll move to the last question. 7. Let f from close interval 0, 1, 0, 1 be continuous and differentiable on open interval 0 to 1 such that the function has value equal to 0 at 0, equal to 1 at 1, and we are given that f is not identity. That means fx is not equal to x for every x. That means, or we can say that there exists some point that is, there exists some c in closed interval 0 to 1 such that f of c is not equal to c because the function f is not identity. Also, they are saying that there exists some t in open interval 0 to 1 such that at this point ft is equal to t. Then they're saying, yeah, state whether true or false. There exists some p in open interval 0 to 1 such that f of p is strictly greater than p. So let's see what happens if this does not happen. What will be the scenario if there does not exist any such p? So we'll start with, suppose fx is less than equal to x for every x in close interval 0 to 1. Because if at some point this is greater than, then therefore the given statement is true. So we'll see if this condition can satisfy, that can hold, then we will say that the given statement is false. And if we end up getting some kind of contradiction with our assumption that fx less than equal to x for all x, then we will see, we can say that the given statement is true. So okay, so using this f, let me define another function g, which is x minus fx. Then this implies that this g is continuous in closed interval 0 to 1, differentiable in open interval 0 to 1. Clearly, because fx is continuous and differentiable, and this x is again a polynomial and hence continuous and differentiable. Therefore, the function g is continuous and differentiable. Moreover, we know the value of the function f at some points that will give us g at 0 is 0, g at 1 is 0, g at t is 0 as well. And since this fx is less than equal to x, this implies gx is greater than equal to 0 for every x in close interval 0 to 1. That means if we plot this function g, it is 0 at 0, is 0 at t, it is 0 at 1 as well. And it is always positive. So it can be, there is only one possibility, or we can say two possibilities. Either the function is something like this, or maybe it was 0 before t and then 0, then it went to 1. Maybe it had some other roots as well, but at t we must get something like this. So we'll see that eventually this type of condition gives us a contradiction. How it affects the differentiability of the function g. Now suppose this case happens, the first case, suppose the graph of g is given as this. So basically it is having a sharp end at x equals to t. So in this case, let's see the differentiability of the function g. Now the left hand derivative, which is limit h tending to 0 minus g h, we say gt plus h minus gt upon h. So this gt plus h, since h is coming from negative sides, so that means gt plus h is something strictly positive, and gt is 0. So this is strictly greater than, or in fact, no, I cannot say strictly greater because h is negative. Now this is equal to limit h tending to 0 minus gt plus h upon h. Now since h is approaching to 0 from left hand side, that means we are taking h to be negative. And since g is always positive, therefore gt plus h is positive. In fact, it is strictly positive in our case. Equal to 0 case we'll consider later. So that means the left hand derivative is strictly positive. And what about the right hand derivative? This will be limit h tending to 0 plus gt plus h minus g0 gt0 upon h. Now in this case, since we are taking h from the positive direction, this is strictly positive. Now this gives us a contradiction. The left hand derivative was strictly positive, sorry, strictly negative, na? The left hand derivative was strictly negative, but the right hand derivative is strictly positive, which gives us a contradiction. That means g is not differentiable at t. That means this type of graph cannot happen. So another possibility is that it was 0 somewhere before t and it was kind of constant. Case 2, graph of function g was something like this. See something here. So if this is point C1, this is point C2, in this case, one can see using the exactly same arguments, you can see that at C1, the left hand derivative will turn out to be strictly negative. Yeah, as we were seeing earlier. And the right hand derivative will come out to be equal to 0. So this will affect the differentiability of g at C1 will be affected. Because we know that the function g is differentiable in whole 0 to 1. Therefore, it should be differentiable at C1 as well. But from in this case, we'll get loss of differentiability at C1. And also at similarly using the same thing, you'll get loss of differentiability at C2. Therefore, the only possibility for the function g to be differentiable everywhere is that it should at some point come to the negative, the fourth quadrant. That means its value should be negative at some point. So therefore, in all the cases, if gx is always positive, then we have some loss of differentiability. Differentiability, which gives us a contradiction. Hence, there exists some p such that gp is strictly less than 0. That is, p minus fp is strictly less than 0. That is, p is strictly less than fp. That's what they were saying. That means their statement was true. I hope this is clear how we are getting this p to be strictly less than fp at some for some p. So that was mainly due to the fact that the given function f is differentiable. The function f is differentiable everywhere, and hence the function g is differentiable at all the points. And in order to preserve this differentiability, we must get the graph of the function g to be something like this. Therefore, the given statement is true. I hope this is clear. In the previous problem, I would like you to do all the calculations yourself in notebook using pen. And please, in the next class, let me know whatever the answer you were getting. This is true for the fact that this partial derivatives will exist, but just let me know what will be the exact value so that I can match that with my own calculations and eventually will confirm the solution. Okay, so if you have any doubt, you can ask, or else we can finish this session. Okay, then if there is no doubt, we'll meet next Saturday with next set of problems. Thank you.